Okay, hello everybody. I'm Dave Turner from the Economics Department at the OECD, and it's my great pleasure to welcome you back to the second day of the OECD Expert Workshop on Economic Modelling of Climate and Related Tipping Points, and to introduce this session on modelling the impacts of climate-related tipping points on the macroeconomy. So we have, in this session, we have 4 great presentations lined up for you. Given that we have 4 presenters, what I'll plan to do is introduce each of the speakers one at a time. They'll give their presentation in 18 minutes or less, and then we'll move on to the next speaker. Please send your comments and questions in the Q&A box, and judging from yesterday, there's a lot of activity there, so you might get answers to your questions directly there. So please make use of that. And where some of the questions seem most pertinent, especially applying to many of the presenters, we'll take some of those questions at the end as well. Except maybe if I spot a burning issue or something that needs urgent clarification, and then I might try and fit in the odd question between presentations. Okay, so what I'd like to encourage everyone to do though, and that's both you, the audience, and the presenters, is try to link some of the issues that were mentioned in yesterday's sessions to the ongoing presentations. So where are the points of agreement? Where are the complementarities? And just as importantly, where are the contradictions and points of conflict that we need to resolve? So in chairing the session, I'm going to try and do a bit of that myself. So first up is Michael Kiley. He's Deputy Director of the Division of Financial Stability at the Board of Governors of the Fed. He's published widely on a range of macroeconomic issues, and I have a personal recollection of Michael because we were very lucky. He spent some time in his career early on at the US desk at the OECD, and I very well remember his presentations of the US economy as being very clear and insightful and something not to be missed. And so the paper that Michael is going to present today plays a bit into yesterday's debate about level and level growth effects. So if you remember Bill Nordhaus's presentation, Bill showed that a specification where the level of temperature affected the growth rate of GDP could imply massive GDP losses, especially for poor countries. And I guess he was suggesting that that was probably implausible and inconsistent with history. Now, I think a rejoinder against the alternative level camp, and here I want to try and paraphrase and take out of context something Lawrence Boone said when she was chairing the first session, is that often the level approach seems to produce damages which are only a few percentage points of GDP many decades out. And I think, as Lawrence said, if I'm not misquoting it, why would policymakers care about that level of damages? Well, more importantly, where does Michael's paper fit into this debate? Well, I think he's got one foot in the level growth camp, but it's not quite as straightforward as that because Michael's modeling growth at risk, but much better that Michael explain. So over to you, Michael.
Thank you very much. I'm really happy to be here. It's an honor to be included on the program, and it's a special treat to be presenting back at the OECD. It has been 2 decades since I spent some time in Paris, and it was a great opportunity for me to grow as an economist, and I'm happy to be back to present my research today. Let me share my screen, and I'll be going through my work on growth at risk from climate change. I think importantly, and as stated on the first slide here, the views that I present today are my own and do not reflect those of the Federal Reserve or its staff. This is very much a research paper meant to contribute to the research literature on the links between climate and growth, but not meant to reflect any policy views or intentions of the Federal Reserve. That said, part of the reason why I became interested in this set of issues, is very much related to the theme of this session. and the implications of climate change for macroeconomic policy and financial stability policy. So I have been involved in working groups at the Financial Stability Board, the Federal Reserve, and through the Financial Stability Oversight Council here in the States on climate change and financial stability. This is very much a research paper, but it is those pressing issues that pulled me into this literature. So let's start with the motivation for my talk. And, based on the conversation over the last, day and then continuing this morning, I don't think the motivation is very, very difficult for this audience. Climate change is perhaps the central economic and social challenge of the 21st century. Right? It will affect the lives of everyone on the planet. The current Secretary of the Treasury, Janet Yellen, has often called it an existential threat to the planet. And she's just building off of others. But climate change is a very important issue. Rising temperatures, shifts in precipitation, more frequent and severe extreme weather events and natural disasters, sea level rise, among many other changes induced by climate change may impact economic activity. What I'm going to look at is very much related to the literature that Dave discussed, the literature on sort of damage functions of how does shifts in climate affect economic activity. But I'm very much going to focus on a particular aspect that has not been explored, and that is how these changes may alter the risks to economic activity. Right? So much of the literature focuses on what might happen over the course of decades to a central tendency, and I'm going to be looking at the whole distribution of economic activity and ask what sort of risks may accompany climate change. The contribution of the paper is relatively straightforward. I take an approach very similar to several of the papers that were discussed yesterday, but I'm going to use that same approach to examine risks to economic activity associated with climate change across a large panel of countries. After doing that empirical analysis, I will illustrate the growth at risk from climate change under a few representative concentration pathways. I'll be using the RCPs, prior to the most recent IPCC report. These illustrations, I think, are very helpful, right? Because, it's hard for folks to grasp. Well, exactly what do you mean that the fifth percentile of growth is going to be lower by X percentage points? What does that look like? And I think the illustrations, the figures, will make it really clear that growth at risk from climate change is large. In particular, growth at risk is very large in low income or hot countries. And in particular, what that means is that severe economic contractions may be more likely in the future owing to climate change. Right? So it's not just that growth will be lower, but that the possibility of growth disasters in any given year will be much higher. So this is somewhat different than the previous literature. In the previous literature, much of the impact of climate change on growth, it's certainly been examined extensively and in a number of ways, in IAMs, the most familiar example to many, especially not experts in the literature, is the Nordhaus-Dietz model. Right? It's also been examined in a variety of other more reduced form approaches that simply link growth to various proxies for climate. And here are a range of papers. I'm going to be following, this second approach, this reduced form regression approach. Importantly, this research has used weather, right? Typically temperature and precipitation, because those are variables for which it is relatively straightforward to get large cross-country data sets for long time periods. Right? The research has used weather to proxy for the effects of climate change, and it's not a straightforward decision, right? It may or may not be a good guide to the effects of climate, as has been discussed in the related literature, right? And why may temperature or precipitation, year-to-year fluctuations in weather not be a good guide to the effects of climate? Right? Well, climate change will be associated with persistent changes in various aspects of the weather. Those persistent changes may allow, for example, opportunities for adaptation over time, which are not present in year-to-year fluctuations. Right? It may be very difficult to adapt to a one-time extremely hot year, right? And it may be relatively straightforward to adapt to an increase in temperature over the course of decades. I think there are counter arguments, and the literature certainly talks about these, but it is an important thing to think about when one asks whether or not the empirical results are plausible. And I think this goes back to this is related to the observation that Dave made at the start of the session, that in some of these growth regressions, if they get projected out 80 years, the effects on GDP are very, very large. The coefficients in this reduced form literature on the links between temperature and growth, they can be quite large. And I think some interpret that as a misspecification. That's certainly the subject of the Newell, Preston, Sexton paper, where they extensively investigate the sort of levels versus growth issue in these reduced form damage function specifications. But I think it's also sort of fundamentally related to this identification problem of, should we be extrapolating year-to-year fluctuations in temperature to proxy for the effects of climate? It's a difficult question. Climate and weather are not the same. Importantly, the research that exists is primarily focused on average expected effects. So, right, what have they done? They've run a least squares regression, right? That is an estimate of the mean, right? When you minimize the sum of squared errors, you're looking for the mean of the distribution. Right? I'm going to look at something different. I'm going to look at the entire distribution of economic growth, as in the growth at risk literature. It's going to be very similar. So this slide just throws up what the equations look like. There'll be a quantile regression that links growth and various proxies for weather. Today, I'm just going to focus on temperature because that is the important variable that I found, and really consistent with the previous literature. Precipitation is not particularly important in these cross-country growth regressions. The regression regresses the year-to-year change in GDP in a given country, J, on country fixed effects, a set of time and region fixed effects, or time trends, in order to extract other factors that may be influencing growth, and then various functions of temperature. And the literature has explored a variety of different functional forms for temperature. So one specification is quadratic in temperature, right? That's the Burke, ZHANG, and Miguel paper. They argue that there's sort of an optimal level of temperature, that something around 13 degrees Celsius is the sweet point for economic growth. That's, for example, the average temperature in the United States. And that regions of the world that are hotter are more sensitive to fluctuations in temperature and have lower growth, or regions of the world that are much colder are more sensitive to temperature and have lower economic growth. Right? So that's what a quadratic specification gives you, sort of an optimal temperature, and then increasing damages as one moves away from that temperature. A second specification is quadratic, but includes interactions for the change in temperature. This is related to the levels versus growth specification, although I'm not going to talk much about that issue. It also helps to say, well, is it the year-to-year fluctuations in weather that are driving growth, or is it the average movements in weather? Right? Is it that it's really hot this year, but it was cold last year? Does that have a different effect on growth than just if it's hotter? And that's the convened specification. That specification actually gives very much the same results as simply a quadratic in temperature. The interactions are not important. And then the final specification is that there's a linear relationship, but it's just different across low and high income countries. So this is the specification in the paper by Melissa Dell and co-authors. I include all of these. Actually, the results are going to be extraordinarily similar across all of them, and there are good reasons for that. I can say that, there's actually a lot, people have very strong feelings about which specification one should adopt. What I really want to emphasize is that, across the countries that I'm interested in, or actually across all the countries in the sample, results are really, really similar regardless of the specification. And that's because, frankly, rich countries tend to be temperate countries and poorer countries tend to be hotter countries. That's been observed in the cross-country growth literature since the 1700s, and it remains true today. And even after accounting for country fixed effects and other factors, which specification is chosen does not really matter. So the data I'm going to use is just from the replication data set of Burke, Davis, and Diffenbaugh. Covers 124 countries for the 50 years from 1960 to 2010. I focus on the growth of real GDP per capita, and the temperature variables used, are detailed, sort of very geographically specific data aggregated to the country level using population weights at those, very detailed geographic levels. Okay, so what are the first sets of results? Well, these are just replication results that essentially are more or less identical, it's a slightly different data set to the Burke, ZHANG, and Miguel, or the Dell, Oken, and Jones papers. And that is that the effects in hot countries or in low-income countries of a 1 degree Celsius increase in temperature are large. So a 1 degree Celsius increase in temperature lowers growth by about 1.25 percentage point. That is a very large effect. And as Dave noted, if you were to extrapolate that, that's for 1 year. If you were to extrapolate that effect out for 50 years and used that, but you would find that growth is GDP is 60% lower in a hot or a low-income country because of a 1 Celsius degree increase in temperature, which is certainly what is expected, even in some of the most optimistic representative concentration pathways. What I am interested in is the effects on the entire distribution of growth. And this table reports results by growth decile for those same regressions. And again, the results are very similar irrespective of specification. And so I just want to emphasize that here, this median regression, these are results analogous to the results in the literature for the central tendency. And that is that growth is about 1.25 percentage point lower for the central tendency of growth. But the downside risk to growth is actually much more sensitive to temperature than the median, right? So that the coefficient is about -1.9 or -1.7 percentage points for the 10th decile, right? So a 1 out of 10 year growth rate is on the bad tail is much more sensitive to temperature than an upside growth. In fact, the upside growth is very insensitive to temperature, right? So what we can expect in a hotter world associated with climate change is that there will be years with much lower growth disasters, but there won't be very many years with better growth, right? That's not, we're going to see a tilting of the risk distribution towards worse outcomes in addition to lower average growth outcomes. So why don't we walk through a couple examples of the implications of these sort of specifications for growth at risk in some different countries. So for the US, right, the US is a high income country. Right? The US is a moderate temperature country. Its average temperature over the last 50 years has been about 13 degrees Celsius. Right? That's actually, in these specifications, that's estimated to be the optimal temperature for economic growth. So growth at risk in the United States is low. It's high income, so maybe it's able to adapt to climate change well, right? Irregardless of the reason, it's at what these regressions say is the optimal temperature, and it's high income, so its growth at risk is low. Brazil, right, is actually considered high income, right, because there's only 2 buckets in this regression, high and low income, and so it's whether you're an above median or below median income level country for the globe, right? And Brazil is above the median. So Brazil is a high income country, but it's also relatively hot. Its average temperature is about 24 degrees Celsius, right? As a result, whether its growth at risk is high or low does actually depend on which of these two empirical specifications is right. And the paper does not take a stand on which specification is right. Brazil is one of the countries where it really matters. Does it matter if you're high income, or does it matter if you're already hot and are going to get hotter? In contrast, countries like India and Nigeria are low income and high temperature. And so growth at risk in countries like India and Nigeria is extraordinarily high, irrespective of the empirical specification, according to the results in this paper. So what does it mean to say that growth at risk in India is extraordinarily high? And so here I plot the economic growth distribution. This is GDP per capita for India over the 1986 to 2005 period. And so this is estimated via kernel density. It's the black solid line. So the median growth rate has been a little bit over 4% per year, right, in GDP per capita. There are some years, but they're relatively rare, in which GDP per capita falls in India. And there are some years in which it grows very, very rapidly over this 20-year period. Under representative concentration pathway 2.6, the temperature in India will rise by a little bit more than 1 degree Celsius by 2050. As a result, the central tendency will fall to about 3.
2 minutes, Michael.
Thank you. Will fall to about 3% per year. Right? That's the shift in this line. Right? But importantly, the entire distribution fattens on the lower tail. Right? So upside growth surprises will be about the same probability, a little bit worse. Right? But those are relatively insensitive to temperature. But growth disasters, right, the chance of GDP actually falling on a per year basis in India increases dramatically. And under representative concentration pathway 8.5, where the temperature in India rises by much more by the year 2050, right, the central tendency of growth in India falls somewhat further, but importantly, true growth disasters increase dramatically. Okay. So the risk of extremely poor outcomes for economic growth in a country like India is increasing dramatically according to these specifications with climate change. Why do we care about something like this, right? Should we just focus on the average effect? Obviously, the average effects are very important, particularly if they compound over time, as Dave talked about at the beginning of the session. Nonetheless, many of us on this call, Dave and others included, are macroeconomists, right? And we know that when there is a growth disaster in a country, there are extreme social and economic implications, right? It is very costly in terms of welfare to see widespread unemployment, declines in income, right? And those sorts of things are going to be, according to these regressions, much more likely in a world where climate change worsens. And under every possible projection, climate change will worsen from current levels. So to conclude, I've looked at growth at risk from climate change using the sort of quantile regression approach that has become used in other areas of macroeconomics. I have a paper coming out in the JMCB on unemployment at risk in the US that uses similar sort of empirical approaches. According to the specifications in this paper, growth at risk from climate change is potentially very large. In particular, the effect of climate on growth are much larger for downside risks. Right? So that climate change may make severe contractions in economic activity more likely. Of course, this is simply a reduced form regression. This is not a structural model. I haven't done any analysis of why this is the case. And the reduced form regressions may lead us astray, right? They may not account for room for adaptations or other factors that may lead this sort of approach to overstate the downside risk, of a severe economic contraction associated with climate change. Nonetheless, the results are pretty strong in terms of statistical significance and economic significance. And as a result, clearly more work and focus on this topic is needed. And that's it. Thank you.
Great. Thank you, Michael. I just have one burning question, and it's also in reference to a paper you mentioned and Shardul and Bill Nordhaus mentioned, which is the Newell et al. Paper And I mean, my interpretation of that is they ran lots of regressions of the level growth type and came up with the answer that the results are all over the place. I mean, you're claiming with your specifications that they're very robust. Can you give us some insight as to why your results are robust, whereas they find the opposite?
Yeah, so I think this is a great question. Actually, I'm continuing to work on this, and so I need, to confirm the following. I don't want to say that the following is the answer, but I actually think the answer is pretty simple, right? They're concerned about what is the effect on the level of GDP 80 or 100 years from now. And right, my background is econometrics. It's very difficult to determine the size of the quote unquote permanent component in GDP and how that's affected by economic variables. It's extraordinarily difficult to forecast 100 years in advance, and whether or not you adopt a specification where anything in your specification is purely temporary, sort of stationary specification around the trend, or adopt a specification in which there are permanent effects of shocks and then extrapolate them over a very long time period. If you're using a data set of 50 years, and then you want to extrapolate out another 50 or 100 years, the data are just extraordinarily uninformative about those permanent effects. Like, that is a fundamental econometric challenge. It's been well appreciated, since the literature on unit roots and macroeconometrics developed in the 1980s, right? And there are a lot of papers on that. It's just extraordinarily difficult to differentiate between a permanent effect and effect that lasts 10 years. Right? That's extraordinarily difficult econometrically, especially in a sample of 50 years, right? If the difference between, right, just to illustrate this and drive it home, if you have a sample of 50 years, you have 5 observations of what happens over a 10-year period. Right? And what we're talking about is extrapolating something that's going to happen over a 100-year period, where we have 0 observations. It just econometrically is really hard. Why is it different in what I'm doing? I'm just asking, well, what's going to happen to the year-to-year fluctuations in growth? Right? Are there going to be very bad years? And that it doesn't matter that much whether or not your specification is good at picking out the 100-year effect or not. It's just, you're just trying to gauge, are there going to be really bad years or not? Not are there going to be permanent scarring that might be really large or somewhat or small. So I think it's just, that challenge that the unit root literature taught macroeconomists, 30 years ago. It's just really, really hard. But I'm looking at the 1-year changes, not the 100-year changes. And in my data set, I have 50 1-year changes for each of 124 countries. And so the data is more informative.
Great. Okay. Thank you, Michael. I think a very, very stimulating paper. So let's move on to the next paper and presenter, who is Professor Jean Pisani-Ferry. He holds a chair at the European University Institute. He's a senior fellow at Bruegel and at the Peterson Institute. As well as being an academic, he's a professor of economics at Sciences Po. He's got a distinguished career as a policy advisor. And I think on top of that, Jean is one of the great communicators in the economics profession. He's published widely on policy, and particularly European policy issues, and he's an active contributor to public debates and has, for example, regular columns in Le Monde. So the paper Professor Pisani-Ferry is going to present, I think very usefully, in a sense, cuts through this debate about what the likely long-run GDP effects are of climate change. And he focuses on the nature of the medium-term macroeconomic shock, which I think is more inevitable. Professor Pisani-Ferry, I'll hand over to you.
Can you hear me? There's something going wrong here. I'm on mute.
We can hear you. We can see your slides, but they're not in presentation mode yet.
Okay. I thought I was muted. Sorry. So let me move to presentation mode. And do you see the presentation? Not the right one.
But it's not in presentation mode.
Okay, sorry for that. It's always. Should be good, right?
Yeah.
Okay, sorry for that. My presentation, and really thank you for inviting me, is going to be quite different from the previous one for two reasons. The first one is that I'm not dealing with the same question, and I'm not actually dealing with mainly with the questions that have been discussed so far. I'm dealing with the question of the transition and how the transition can affect the macro outcomes. So not how climate change affects macro outcomes, but how climate policy may affect it, which is clearly a very different question. The second reason is that it's not original research that I'm going to present. It's more a commentary on what we have and the type of discussion we're having on these issues. Actually, this is a note published by the Peterson Institute, a short policy brief that grew out of my frustration with the type of discussion we're having on the interdependence between macro and climate policy. So basically, the reason is the following. Okay, there really, to put it simply, there are two ways to think about the transition. One is to imagine a sort of smooth inflection that gradually, climate policy affects the nature of investment, the nature of the energy system, the consumption patterns, etc. But that's a fairly gradual process. Therefore, that may have implications in the long term, but doesn't have strong implication in the short to medium term. The other one is to think about it as a sort of turn that forces to slow down and has immediate implication. And I think for good reasons, because because economists had to integrate the climate dimension in the sort of the long-term thinking, the first approach has been fairly dominant for quite some time. And that has affected not only the sort of type of results, but also the very methodology through which climate issue is being approached. Now, what we're facing now is a sort of precipitous change in policies, having to do with the target of limiting the rise in temperature to 1.5 or 2 degrees. And since policy procrastinated for so long, it requires a sharp turn. And the question is how this sharp turn is going to affect the macro performance is, I think, a question that has come to the top of the agenda. And surprisingly, it was not so much discussed. Essentially, if you start from the type of thing the macro community, let's think of the international organization, the treasuries, etc., the type of thing they were doing, the type of reflection they were having, it did not integrate this climate dimension for the medium-term horizon until very recently. It was an issue for, beyond the horizon. So now we're facing something different. Climate policy has become much more macro policy. And that, as I just said, has to do with the, the fact that we're facing a sort of too late, too sudden transition. I'm quoting from a ESRB paper already 5 years ago, who said that it's even more true now than it was at the time. Now, I'm not, again, since I'm dealing with transition issues, I'm not dealing with longer term issues. And I think I would like to emphasize that there are some good news. I mean, you know, if you look at the long term, the way we think about the transition and the economic consequences of reducing emission has changed significantly with research, especially by Acemoglu and others, about endogenous technical change and the way directed technical change towards cutting emission towards a sort of green transition has resulted in a precipitous decline in the cost of reducing emission, which is extremely good news. So that's a sort of, for the longer term, the good news part. The good news is also that, as I was saying, too late, too sudden, the long procrastination. This long procrastination, I wouldn't say it's coming to an end, but there are significant changes. And the EU's recent decision to cut emission by 55% already by 2030, well, not exactly the decision, the proposal by the Commission, but which formed the basis of the Commission proposal to the Member States, and the Member States' commitment to climate neutrality by 2050 represent a significant acceleration. The third, I think, piece of good news is that investors have shifted, and the IEA recently published, together with the Imperial College, an assessment of the valuation of the returns, total returns on green and brown assets based on a large sample of companies, and the fact that you're seeing the valuation of green assets being much higher now than the valuation of brown assets is an indicative of the fact that the private economy is changing gear. Now, we all know, I won't teach anything to anyone here, that nevertheless, the avoidance of catastrophic developments of the type of development we've been discussing so far in this webinar requires a very sharp change in the pace of the decarbonization, which is illustrated by the graph on the left, showing how fast it has to change, and the numbers on the right taken from a recent Google paper, looking at what it implies for the world economy to achieve net zero by 2050. So the question then is, how can we think about the implied shock? And I think the implied shock is a combination of several shocks, having to do again with the policy change. One is the adverse supply shock, which is that part of the capital stock will be priced out either by explicit carbon pricing or by regulation. It's a bit immaterial whether it takes place through carbon pricing or through the prohibition of some type of equipment or new standards, etc. That means part of the existing capital stock has to be replaced, and the existing capital stock, in the case it takes place through pricing, is facing the change in relative prices, that the type of which we experienced at the time of the oil shocks, when change in relative prices had these major supply side effects. There are also distributional effects. They're very much in the news and the attention of policymakers, but perhaps more than the supply shock dimension. The uneven exposure of households to climate change and the uneven exposure of countries. There will be a positive investment shock to the extent the climate policy is successful. There need to be new investment to replace the obsolete capital, the capital made obsolete by the policy. And then there will be a reallocation of capital, reallocation of labor, reallocation of technology across companies, across sectors. And something I'm not going to discuss here, the trade shock or the international dimension. I think the oil shock are an interesting precedent to look at because the oil shock was a sudden repricing of a previously underpriced resource. And that's the type of thing actually we're looking at. So some numbers just to illustrate what I'm saying. The world price of carbon, according to the IMF, is $3 per ton. If you're taking into account existing taxes on fuel as well as subsidies, actually, you come up with something that's closer to $10 per ton. And this is to be compared to the target price for carbon, for which we have different estimates. We have the Stiglitz-Stern one, $75, and then much higher ones by the NGFS, by the Kiné Commission in France, by the Bank of England, which are basically shadow prices derived from the quantity target and estimating what would be the price corresponding to this quantity target. So I took the sort of the lower estimate, the Stiglitz-Stern one, $75, applied to the total emission, and that results in a total levy, if you wish, or nominal levy of 3.1% of global GDP, which I'm comparing to the size of the first oil shock, which was at the time 3.6% of global GDP. So this suggests that there's something in common, not only in qualitative terms, but perhaps also in quantitative terms. So I'm going to qualify this. The evidence of an effect of this sort is also provided by some econometric estimates of the impact of changes in the price of carbon. I'm quoting here a recent paper by Diego Cansec, looking at the impact of changes in the ETS market triggered by EU regulation, and he finds a significant macro effect. Now, to qualify the shocks, as I said, I'd like to sort of look at the distribution of this shock. So this is assuming a sort of full carbon pricing of the emission for countries of the world in percentage to nominal GDP. And as you can see, there's a wide distribution with essentially the advanced countries being on the right because their GDP is less carbon intensive than those of the emerging countries. Emerging countries in the middle, where the carbon intensity of GDP is the highest, and poor country on the left because of the relatively lower carbon intensity. So that suggests that the shock, in fact, will be less than what I said for advanced countries. It will be higher in some emerging countries. It can be very large in some emerging countries. We have some sort of an inverted U-curve. If I look closely at what the shock was for the advanced countries in '73, I find that it was of the order of magnitude of 3% of GDP for several advanced countries and more for some of them. So, which suggests that compared to the shock I'm sort of mentioning, we were in this type of situation, but emerging countries were often suffered a much lower shock, a much smaller shock. So that's a caveat we should keep in mind. The other caveat is that the shock should be less damaging for advanced countries for a variety of other reasons. Well, it's certainly, there was an advance warning about this shock coming, so it's less sudden and unexpected than in 73. It won't redistribute income away from advanced countries toward low marginal propensity of consume foreign economies, the oil producers at the time. That's where the component of the recession that was triggered by this shock. There's already carbon pricing in some part of the private sector. We have this endogenous technical progress that has already been set in motion. And also, from a strictly macro standpoint, the research, for example, by Blanchard and Galli 10 years ago showed that the ability of advanced economies to sort of weather the shock was much better in the 2000s than in the 70s, controlling for the size of the shock, in part because of lower real wage rigidity and in part because of the policy reaction. So it's still a supply shock, but perhaps a less severe one than what the numbers would suggest. Let me, in the interest of time, skip the distributional effect and go to the investment implication, which is sort of my second big shock. So we have, from different sources, an estimate of how much investment it would require to get to carbon neutrality by 2050. So I'm using here, estimate by the IEA, by the IMF, by the European Commission, and by the British Climate Change Committee. And basically, they all converge more or less to say that the additional investment, and I'm emphasizing additional, by 2030 is of the order of magnitude of 2% of GDP. Which is large. If you look at the evolution of the world investment rate over the recent decades, it has lowered by less than 2 percentage points. So basically, it would reverse or more if climate action were implemented globally. It would more than reverse the change in the investment to GDP ratio globally that has been observed over the last 3 decades. Now, if you look more closely at what happens in, for example, the IEA estimate, which are detailed in terms of what the composition of this investment, what you're seeing is that not only there is this additional 2 percentage point investment that's taking place in the simulation, but also you have a reallocation from brown investment, fossil fuel investment to green investment. So on top of the macro effect, you have this reallocation effect. The British analysis by the Climate Change Committee is interesting because what they do is that they compare the amount of investment that's needed to achieve climate neutrality.
Professor, 2 minutes, please.
Yeah, 2 minutes, absolutely. To the actually decline in operational costs over time. And so I did this graph just to show the cumulative investment net of operation cost reduction in the UK along the net zero pathway. And this is a percentage of GDP. So it's actually culminates at 15% of GDP, indicating again that we're speaking of something really meaningful macroeconomically. So the macro implication of such an evolution of investment that we're facing on the one hand a negative supply shock, and we're facing on the other hand, we will be facing on the other hand an investment shock. So that means reallocation of output away from consumption towards investment. And again, I mean, you know, if you do it at the world level, that's simple because it's a closed economy. That means 3% less consumption by 2030, which is again a significant number in terms of the welfare implication. And there are also risks along the transition, especially on the intensity of the reallocation depends on the credibility of climate policy. The IEA emphasized this question very much, that the risk in its recent report published last week, that the risk is that not enough green investment, but perhaps you know, already not much brown investment. Finally, on the public finances, I think this is a significant topic for investigation. The fact that the traditional view was that Pigouvian taxation would yield revenue, and that the question for public finances would be to sort of define what the best way of using these revenues, most likely to cut taxes, especially on labor. That was the theme of the double dividend. So what I think we are seeing more and more likely is the fact that the revenues won't be that significant, that mostly states will proceed through regulations, through subsidies, through public investment, and that instead of being a net positive for public finances, the climate policy risks being a net negative for public finances. So to conclude, if I compare the way we think today about these consequences of climate action with the way we thought about it 5, 10, or 20 years ago, I think we're probably more optimistic today than we were about the long-term cost of this transition. But I think it's also a more urgent task, and the transition cost, shock, sorry, I think we view it today as more significant for all the reasons I gave, and let me just repeat: the adverse supply shock, distributional consequences, the investment, and the fact that there needs to be reallocation away from consumption to investment, the public finances shock, and the instability along the road. So I think I would sort of argue strongly in favor of us working much more on these dimensions over the medium-term horizon. Thank you.
Thank you very much. That was very stimulating. I wonder if you could just spend a minute or so more saying what get prepared means. And I wonder also in the context, we're seeing surging energy prices at the moment, which might be a different phenomena, but if you read the media, then some of the sort of reactions that are being discussed are more regulation. So what would be the advice briefly to better prepare for the
advice briefly would start with some, I think, more realism in the assessment of the consequences of this transition. I think too often the simulations that have been used by policymakers were based on the assumption that there was no significant supply shock. So therefore, that the green investment would essentially be expansionary, and that all the problems having to do with labor reallocation, all the question that I'm asking would sort of be made much easier by this sort of Keynesian boost. And I think, you know, I wouldn't exclude that there's some, depending on the country, there can be some slack. But I think, you know, on the whole, it's not a sound assumption that just to neglect the supply side, the adverse supply side consequences of this. So that would be the first thing I would say. The second is perhaps to sort of, you know, look much more closely to these reallocation dimensions and get prepared also in terms of finding out what are the likely consequences and the policy responses, you know, once you have identified the problems. What's more difficult, but that was very much also the topic of what we're discussing here, is all the instability that may be created along the way. And that's a question for monetary policy, for example. The question for monetary policy is less, what will be the sort of overall cost of this transition, but much more what are the consequences for monetary policy in terms of instability along the road.
Great. Thank you very much. So time is marching on. I think let's move to the next presentation. So the next presenter is Sandra Batten, who is a senior economist in the Monetary Analysis Directorate at the Bank of England. Her research focuses on the impact of climate change on the macroeconomy and the implications for monetary policy. I can personally recommend two overview survey papers that she's written with colleagues at the Bank of England on the economics of climate change, and that are published as Bank of England working papers. But the presentation today that Sandra is going to make uses scenario analysis to look at climate-related risks and economic tipping points from the perspective of a single country, and in this case, the UK. Over to you, Sandra.
Thank you very much, Dave, for that great introduction. And thank you very much for inviting me to this great event. It's a real pleasure to be here. Let me share my screen. Can you see my screen? And now I'm trying to put my camera back on. Yeah.
All good. Over to you.
All good to start. So again, thank you very much for inviting me. Please remember that the views presented today are my personal views only. They do not represent the views of the Bank of England or neither of its three policy committees. I'm going to talk about economic impacts from climate change, and I will show some examples of how we can think about climate-related economic tipping points using a mixture of my own research and some descriptive analysis. These economic tipping points can be caused by physical climate risks, such as extreme weather events, as well as from climate transition risks, in particular mitigation policy. In my presentation, I will focus on the UK, and I will discuss things from a monetary policy perspective in the sense that monetary policy requires us to assess current macroeconomic conditions, and any climate change manifestation that affects the economy in the short to medium term is therefore relevant for monetary policy. We also need to be paying attention to the buildup of any imbalances that could lead to macro financial tipping points, and this could very well be caused by climate change. So starting with the physical impacts, these are some of the studies. They use weather data to infer economic impacts of climate change, and there are many more, including Michael's that we just seen. Regardless of the climate change aspects, studying the short-term impact of the weather on the economy is part of the routine assessment of current economic conditions. And as climate change leads to increases in the frequency and severity of extreme weather event, this kind of analysis will become even more important. Global studies, we've heard yesterday, can mask heterogeneity within countries and across industries. It is important to look at more granular level. So one example is the study by Colacito and co-authors for a panel of US states. And in the next few slides, I'm going to describe the results of a similar analysis I did for the UK. First, I ran regressions of annual GVA growth on weather variables for a panel of 179 UK regions. Like Colacito and co-authors, I find that when using average annual temperature and precipitations, like in column 1, the coefficients are small and not statistically significant. When instead I use seasonal averages, as shown in column 2, the impacts are larger and statistically significant. Therefore, at the first level of aggregation, that is, if we use annual averages instead of seasonal ones, we are already missing out of some of the impacts. Next, I ran the same regression for regional GVA growth, but for a number of industries separately, and I find striking heterogeneity in the results across both seasons and industries. Here, the horizontal line within the box is the coefficient on temperature for a given industry weighed by the share of the industry GVA in the total. The boxes are the 90% confidence interval, therefore taller boxes indicate less precise estimates. Temperatures affect some sectors very differently depending on the season. For example, output in the real estate sector, in red, is boosted by warmer winters, but reduced in warmer autumns. And it is not affected by temperature changes in summer and springs, which are already the hot seasons for the housing market. The table on the right shows the weighted average coefficients. Overall, the negative effects in summer and autumn are balanced by the positive effects in winter and spring. Therefore, looking at the table, you might conclude that a 1 degree increase in average temperatures would have positive economic effects. Over the next decade, UK temperatures are projected to increase during the summer, but fall in the winter months, at least in the RCP 2.6. Based on the historical relationship I estimated, this projection implies future negative economic impacts in both climate scenarios. Of course, the weather-economy relationship might not remain constant in the future, for example, in case of climate adaptation. The estimated impact of precipitation on regional GVA growth is similarly heterogeneous across seasons and industries. The estimated relationship of the past 2 decades across sectors suggests that the seasonal effects cancel out, as you can see in the table. Precipitation are projected to increase in winter months and decrease in the summer months, so the total annual effect remains balanced. However, heavy winter rainfalls are associated with higher risks of flooding, which could have nonlinear effects and become a source of economic tipping points. So to summarize, heterogeneity is important, and aggregate studies can miss important sources of heterogeneity, such as local, sector, and seasonal variation, which might be relevant for tipping points. Economic tipping points are more likely to be found on small system scales. However, it is important to understand aggregation effects. Small-scale tipping points may be absorbed at the aggregate level or may lead to larger scale economic impacts, especially in vulnerable regions. One can think of many more examples, such as a collapse of entire economic sectors like agriculture from farm abandonment or tourism. The impact of ecosystem stress on essential economic resources is something that, in my view, requires a lot more thinking. Moving now on the transition impacts. A useful tool here is scenario analysis, which is used more and more by central banks for climate stress testing of a financial system. These scenarios offer a top-down approach to assessing the impact of climate policies on the economy. The left-hand side chart shows 3 of these possible scenarios, which were developed by the Network for Green Financial System and academic researchers, and correspond to different possible paths for the carbon price. According to these scenarios, an early policy action has a small cost per year of 0.1 percentage points in terms of GDP growth. A late transition, however, could lead to around 7% shortfall in UK GDP in 2033 compared to an early action, as shown on the right-hand side. To put this in context, UK GDP fell just over 4% in 2009 following the global financial crisis, and almost 10% in 2020 due to COVID. So this late action scenario is a clear example of a tipping point in which pressure to set a carbon price builds up and results in a higher carbon price and sudden and large GDP loss. There is also a bottom-up approach that focuses on the impact of specific climate policies on different economic sectors. Before I can discuss this approach, I need to spend a few minutes describing the setup of UK climate policy. The UK is committed to achieving net zero emissions by 2050 and to front-load the target to 75% reduction by 2035, and this is shown in the black dotted line on the chart on the left. This target is consistent with the Paris Agreement in the sense that if it was replicated across the world, together with ambitious near-term reductions in emissions, it would deliver a greater than 50% chance of limiting the temperature increase to 1.5 degrees Celsius. What is important here is that the UK has a well-defined legislative framework for climate mitigation and adaptation, starting with the Climate Change Act of 2008, which established, among the other things, the Climate Change Committee, an independent statutory body that advises the UK government and the devolved governments on emission targets, and has access to a wide range of expertise. Emission reductions are then achieved through a series of 5-year carbon budgets recommended by the committee, and these are shown on the vertical bars on the chart around the table. The 6th carbon budget recommendation was issued last December, and the government adopted it in June 2021. So where are these emissions coming from? The left-hand side chart shows that 3 broad sectors, surface, transport, buildings, and power generation, account for around 60% of total UK emissions. As the chart on the right shows, these 3 sectors will require large emission reductions by 2035. And these are the sectors that I'm going to focus on in a little more detail. One challenge with the bottom-up approach is that these broad sectors, which are designed for emission reporting purposes, include both households and business activities and therefore affect components of both demand and supply. And the challenge is to map the broad sectors such as transport and buildings into emission generated by industry and consumption expenditure. So this mapping shows that consumption expenditure accounts for around 30% of emissions. In the next few slides, I will look at decarbonization pathways and see how we could go about assessing their implication for supply and public and private demand. It is important to stress that these decarbonization pathways were put forward as a recommendation by the Climate Change Committee, but have not yet been adopted by the UK government. The government net zero strategy, which is expected this week, will spell out to what extent these recommendations will be adopted. So starting with transport, 50% of carbon abatement is from cars, 80% from more vehicles, as shown in the chart on the left. UK policies to end the sale of all new petrol car and diesel cars and vans by 2030 and hybrid sales by 2035. On the demand side, some combination of emission tax and technological progress will make battery electric vehicles cheaper overall around 2030. So after 25, when all new cars will be electric, there are still 15 years to replace all cars in circulation. And this seems unachievable targets given that the average car is around age is around 8.5 years. On the supply side, ultra low emission vehicles, cars were 10% of all new cars, like the chart on the right-hand side shows, and battery and electric cars were, were only 5.4%. So these will need to get to 100% by 2030. And this is where the bottlenecks might be, with the risk of cars becoming unaffordable, so supply side bottlenecks, or a larger share of consumption having to be devoted to car costs. Moving on to buildings, 70% of abatement is from residential sources, mostly heating. So this transition of domestic heating is perhaps the greatest challenge of all the sectors. The UK ambition is for no new gas boilers from 2035. And given that the average life of a boiler is roughly 15 years, this would allow full replacement without having to scrap existing boilers prematurely. Again, any barriers seems therefore to be on the supply side. There is still quite a lot of uncertainty about the best low carbon technology for domestic heating. And there will be a lack of skilled labor to supply the boilers as well. Finally, the decarbonization of energy. So electricity generation needs to increase by more than 2.5 times to meet future demand by 2050, as is shown on the chart on the left. The net zero pathway decarbonizes electricity generation completely by 2035, and this is shown by the dark blue area, which is fossil fuel generation. There is some residual fossil fuel used by to 2050, which is carbon neutral as is combined with carbon capture, and this is shown in the pink area, and some reliance on nuclear, which is included in the dark yellow area. So renewable energy needs to scale up by a factor of 3 by 2035 and a factor of 5 by 2050. But overall, this electricity mix will be about 3 billion more expensive in 2035 compared to a high carbon system, but will become 5 billion cheaper by 2050. This looks very challenging. However, the trend has already started. As the chart on the right-hand side shows, the share of renewable electricity supply trebled from just over 10% in 2012 to over 30% in 2019. So how can this be achieved? With, as we saw before from John, with large additional investment in electricity generation than the Climate Change Committee has estimated will be needed. This is shown in the blue line on the left-hand side chart. This is higher than historical gross investment of the whole electricity and gas sector, shown in the pink line. At the moment, the electricity sector is a relatively small part of the economy, less than 2% of GVA, and it might need to increase its size significantly. However, it is hard to see this as a major structural shift in the economy, especially compared with the historical changes in this sector. And what are the possible impacts on the public sector budget? Analysts at the Office of Budget Responsibility, the UK official independent fiscal watchdog, have estimated the potential impact of the proposed net zero pathways for the public purse. They had to make certain assumptions about what share of transition costs the government might be willing to pay. And under these assumptions, the net cost of transition represents just 0.4% of GDP in additional public spending each year.
Sandra, 2 minutes, please.
Yeah, I'm nearly done. And by 2050, public sector net debt, shown on the right-hand side, is 25% of GDP, higher than the baseline. But this is somewhat less than the overall increase as a result of the COVID pandemic. In summary, these three sectors I showed you account for around 60% of emission reductions, but over 90% of the costs. The current assumption is the government will fund around 22% of this cost, but this is not yet policy. And in particular, the current assumption that government will only fund 6% of the required investment in energy is quite worrying. So my key takeaways, a large part of the transition involves consumers. In the end, the decision will be taken out of their hand through banning combustion engines, vehicles, and gas boilers. So a large part of the UK transition relies therefore on regulation and incentives to shift consumers rather than widespread market-based instruments. There could be supply bottlenecks, especially in automotives, supply of heating pumps, and lack of skills. The supply side transition, however, is already happening. 10% of new cars are ultra-low emissions. In 2020, 40% of electricity was already renewables. There are risks around financing costs, especially for the energy transition. the energy sector is a small part of the economy and might need to grow. In conclusion, and based on this partial and limited assessment to the UK and the partial equilibrium and more bottom-up approach, but in general, based on this assessment, it seems to me that large parts of the transition involves replacing existing consumption goods and services, such as cars, boilers, and electricity, with their zero carbon equivalent. Therefore, it is difficult, in my view, to see this as a major economic structural change. And this is all I had to say.
Great, thank you very much, Sandra. Just on time. I just had a question which I thought one of your most striking slides was the cost of late action. So just delaying 10 years seems to result in a big permanent loss in GDP. Could you just sort of quickly talk us through the transmission mechanisms? Why does acting late lead to permanent loss in GDP, which doesn't seem to be ever made up?
So that chart is only relevant to the early action, and that is because in the carbon price path, the carbon price needs to be above the carbon price for the early action scenario to the end of the transition. So it's, in a sense, the mechanical consequences of carbon price having to be higher. So the fact the carbon price needs to be higher at every period is because the temperature impacts are driven by carbon dioxide concentrations. So the later you wait to reduce emissions, the harder it is going to be to bring down concentrations, which are a stock, as opposed to the emissions that are a flow.
Great. Okay. Thank you. That's very clear. Okay. Can we let's move on to the final paper of the session, and the presenter is Francesco Lamperti, who is an assistant professor at the Institute of Economics at the Santa Anna School of Advanced Studies in Pisa, where he coordinates the Complexity Modeler Society. He's also a scientist at the European Institute on Economics and the Environment in Milan. And his research interests focus on the intersection between macroeconomics, finance, and climate change economics. And that's what he's going to talk to us about today. Again, it's another paper which is not just thinking about averages, but focusing on risks, and in particular, the link between climate change and financial risks. So, Francesco, over to you.
Many thanks, Steve, for the kind introduction, and I'm very happy to be part of this amazing workshop. I learned a lot during these 2 days, and I hope I can provide also some interesting food for thought. Today I'm presenting the results that we get from a model, which I will spend a couple of minutes in discussing, because it's a model which is relatively different from those that are most diffused in the literature, and it might be that many of you are not really familiar with the technique and with the kind of models that I usually employ for studying the relationship between climate change and the economy. This is a joint work. And I will collect during the presentation the results that are mainly come from 2 papers. The outline of my presentation is rather straightforward, so we'll give an introduction to the issue of financial stability / instability, and then I will try to to show the results that I get from this model in assessing what are the channels and the impacts that climate change might have on financial stability by looking at a specific channel, a specific direction, which starts from physical risk and go to impacts in the economy and then in the financial sector, which will be a banking sector for us. Then I will also try to offer some consideration in climate policy in trying to discuss whether climate policy might be shaped in order to account for these physical risks. If I have time, I'll also try to provide some means into what we are doing on transition risks, and finally we'll conclude. So, financial instability. Sometimes we are tempted to think that financial crises, which are intended here as banking crises, are relatively infrequent event. If we take the perspective at the global level, we can discover that it's not the case. So every year since the 70s, at least a couple of countries in the world, they face a banking crisis, a situation where you have large losses, significant distress in the banking sector, and the government has to step in order to mitigate these risks and to help restoring the standard operations in the banking industry. And we can also see from the picture that these financial crises are usually linked to a real crisis. So the output loss around these financial crises is significant. It's represented here by the size of the bubbles, and it's naively estimated as a 3-year cumulative loss with respect to the pre-crisis trend. But it also entails large fiscal costs. So for the public finances, these crises, they are relevant, and the government on average spends something like 13% of GDP in rescuing potentially insolvent banks and in restoring the standard operation, the normal condition, normal times in the banking industry. And further, it is not just a story of developing countries. It's also a story of upper middle and a high income country according to the Standard World Bank classification. So it is not that the majority of these crises, they happened only in countries where already you have a lot of possible fluctuations. So what we did is to develop a model able to account both for growth and fluctuations, generating endogenous financial crisis, which will be for us potential insolvent, a situation where banks are at risk of insolvency. And then what we do is trying to see whether, including the impacts of climate change, we are able to detect a change in the probability of observing these events. So the literature in a nutshell, as already anticipated by the other speakers, financial stability is more and more a concern for financial regulators and central banks. And I've seen in the literature two broad questions that different groups have tried to answer. On one side, whether the three classes of risk, physical, transition, reliability, even though liability risk are usually left aside, may treat financial stability, price stability, and growth. So whether the central bank central banks should be worried about these risks, and what they can do in order to absorb these risks and to react to the evolution of these risks. In the picture, what you see is a collection of the possible channels that move from physical risks and transition risk, which were also showed in the beginning of the previous presentation, all the way to the financial system. And in the purple circles, what you see is our focus. So in this presentation, I will target specifically physical risks through micro level damage functions. This damage function will affect the real economy. In particular, we will see that they will lower growth and they will alter the dynamics of productivity and the competition in the various markets that we have in the model. And this might affect financial condition of firms in the different sectors. And this might lead to non-performing loans, basically. So the channel that we try to investigate, it's simple, it's just one, and it goes from physical risk to non-performing loans. When non-performing loans, they accumulate in the balance sheet of banks in our financial system, in our banking system, then you might have risk of insolvency, and then we assume that the government step in and rescue the potential insolvent bank. The other part of the picture is this negative feedback loop. So whether different altered financial condition might have a feedback effect on the economy. And what we tried to do in the paper is to estimate the size of this feedback loop or feedback effect. Let me briefly, just in 2 slides, introduce you to the kind of model that I'm using in order to conduct this analysis. So I'm using an agent-based model. An agent-based model is just a computer program which simulates the dynamic evolution of a relationship among ecologies of agents. So for example, we will have a distribution of consumers, a distribution of firms, of banks, of energy plants. And these agents, they interact non-trivially, meaning they do not just interact through markets. And these systems are usually referred as complex systems because you have a sort of lack of symmetry between the micro level and the macro level. So the kind of properties that characterize the behavior of agents at the micro level, they are not useful in order to understand what happened at the macro level. And this is why we have to simulate these models a lot. So what I'm presenting you are results from simulation experiment, extensive simulation experiments where there is basically no optimization. And we study the properties of the system under the different scenarios. What are the key features of these models? The behavior of agents is usually modeled in a direct way, trying to leverage on the psychological literature for what concerns consumers, for example, and on the management literature, for example, for what concerns firms. So usually these agents, they behave according to heuristics and to satisficing behavior, meaning that they do not really optimize their choices. They try some strategy. If the strategy provides some good reward, they keep on the strategy. Otherwise, they change their behavior. So changing the behavior of agents requires time. And there is plenty of empirical evidence that in many, many situations, this is the case. Plus, you have local interactions slash incomplete information. So in our markets, you have asymmetric information, and you have process of learning, exactly modeled in the way that we were describing. Agents, they learn through trial and error, and they evolutionarily select the strategies that provide a higher payoff. And expectation in this context, they are usually adaptive. If you put some of these ingredients together, what you usually get is a behavior which is a sort of disequilibrium behavior, meaning that the system fluctuates, it reaches some sort of steady state where you can observe a sort of statistical equilibrium so that the behavior of the model is more or less stationary, but then you might also see that the system moves away from this equilibrium toward a new one, and you might have also cycles between different equilibria. And it is also a disequilibrium model because usually markets it might be, but usually markets in this model, they do not clear. So as agent-based models being used to study issues related to climate change, yes, a variety of possible issues, mainly linked to phenomena where heterogeneity and interactions that are relevant. So, for example, the consequences of assets trending, in trying to see whether the interconnections that you might have in the financial system might make the risk that mainly originate in a particular sector or in a particular group of sector might become systemic, in the sense that it affects the majority of players in the financial sector. They have been used in order to study diffusion, so where you have different agents that interact and have heterogeneous preferences, and you might have also network effects and imitation effects. So what I will do is to use a particular model, which is called the DSK, which is a macrofinancial model of endogenous growth and fluctuations, which is also an integrated assessment model in a sort of loose sense, meaning that we have a climate module. This climate module takes emissions as an input and returns the dynamics of the temperature as an output. And then we have what we call micro-level damage functions, and I will spend a couple of minutes on them. And in the different part of the model, we have heterogeneous agents. So especially firms, banks, household, and energy plants, they're heterogeneous along different characteristics. And we have networks, physical input-output networks going from firm to firm. And also we have credit networks going from bank to bank. And in another version of the model, which we didn't use here, we also have networks in the banking sector. So networks that arise through the interbank market. The input markets instead, so for energy and labor, these two markets, they're competitive. These models, they are usually calibrated on stylized facts. This means that we have a lot of degrees of freedom, and what we try to do is to select parameters in order to reproduce a large ensemble of stylized facts. By stylized fact, for example, I mean the structure of cross correlations between the main macro aggregates. So, for example, consumption, output, investment. So, like in a similar fashion to the real business cycle literature. But also we try to match stylized facts such as the distribution of productivities that we observe in the microdata. So fat-tail distribution of productivities, fat-tail distribution of output growth. And then we simulate the model in a particular scenario. So along a sort of business as usual slash very hot world scenario. What do we get out of the, oh no, sorry, let me spend a couple of minutes detailing the micro level damage functions that we used. So nothing particular. We in the published version of the paper, we use the simplest climate model we could think about, and it is just a linear projection of the temperature, which depends on cumulative emissions. We tried different models for the climate side, and results are more or less consistent. The only difference here is that since the behavior of the temperature is more or less linear, already in the middle of the center, we observe a relatively high temperatures. And then the damages. So we have firms, heterogeneous firms, which are attached to damages at every time step. And this damage comes from a standard damage function. So this is the damage function that we used. And then we have a little bit of noise here. And in what I'm gonna present, our noise is IID, but we can play with this error term in order to have shocks that are autocorrelated, or they may be spatially correlated, because agents in particular location, they might be more exposed to shocks, to climate-related shocks. And
just go 2 minutes, please.
Okay, yeah, I have to speed up a lot. Okay, so what do we get with this model? I'm not saying this model is able to produce realistic numbers, but I think it's useful to compare the results across the different scenarios with respect to the baseline. Our baseline is a world without climate change. Here you have the number of bailouts observed in every decade that we simulate, and you see that in the baseline we have more or less a stationary behavior. As soon as we introduce climate damages, we have that the number of bailouts, or the number of times that the government has to step in order to rescue potential insolvent banks, really increases. And it increases especially where we target both labor and damages to labor productivity and capital stock. So our damages are in levels at the micro level, but they produce a growth effect. So this is the distribution of the growth rates that we observe in the simulations, the rates of output across the 4 periods of 15 years each that goes from the year 2000, where we initialized the model, to the end of the century. And in presence of damages, in particular damages to labor and capital, what we observe is a flattening of this distribution, so that we can the model experience large contractions, but also large expansions, sometimes in reaction to these contractions, and obviously an average growth rate which is sharply diminished. So what we obtain from a qualitative perspective is that our economy enters a sort of low growth, high volatility regime, where investments are deeply reduced and the instability in the financial sector is much higher. This also brings about a sharp increase in the public debt to GDP ratio. Why? Because we assume that every time the government observes a bank which might be insolvent, it steps in and recapitalize the bank. And then we tried also to understand to what extent this effect is due to the feedback loop. And the feedback loop comes through this equation. So when the banking sector is exposed to higher probability of non-performing loans, it reduces the total amount of credit that it produces to the economy. This means that the economy becomes increasingly credit constrained. And during the simulations, what we observe is that firms that have seen their capital stock reduced, they need to rebuild the capital stock, and so they tend to ask loans to the banking industry. And so this creates a sort of feedback loop, and we estimate that almost 20% of the reduction in the growth rate that we observed is due to this feedback loop. How do we estimate this? By running a counterfactual simulation where we assume that as soon as a non-performing loan appears in the economy, the government immediately steps in and repay directly the firm without having these non-performing loans affecting the balance sheet of banks. Finally, just to conclude, what we find is that macroprudential instruments, they can do something. They are more and more effective in this U-shaped fashion the more temperature increases, so the more damages increase in their size. And we also find that the bailout cost, they increase almost linearly with the temperature. This all made us thinking also whether it might be a good idea to think about climate-based capital buffers. So requiring banks to store a bit of equity in order to absorb risks when they are exposed to firms that locate in particular areas that might be at risk of experiencing damages from the physical perspective. I will just skip to the very last point. We also try to use the model in order to study policy risk. And what we find is that comparing supply side and demand side policies, we find out that the smoothest transition that we can get is when we apply supply side policies, such as bans and regulations on the fossil fuel sector. But however, of course, this generates a cost for the public budget, but this cost is relatively contained. So in order to decarbonize the economy and be consistent with the +2 degrees scenarios, we estimate that the average annual cost for the public balance in developed economies between 1.5 and 3% per year. Okay, I know I couldn't provide a lot of details on this last slide, but I think it can provide some element for the discussion. Thank you.
Thank you, Francesco. I think we're nearly out of time for our session, but I just had a couple of clarifying questions. So the model is, as I understand it, very stylized. So are we thinking about this as being representative of an advanced economy or a low-income economy? And then I guess the other thing that I haven't quite got a handle on is there's greater probabilities of financial crises. Is that stemming from the risk of periods of lower growth? Because I guess when you had that chart up about historical financial crises, we normally think about house price cycles, credit cycles, yield curve. But so what's the link in your model? Is it sustained periods of lower growth? Sorry, over to you.
Yeah. This is the main reason, meaning that when the economy enters this sort of high volatile and anemic growth regime, then you have a lot of entry and a lot of bankruptcies. And this volatility also reduces the pace of investment, and the cumulative exit that you have in the different sectors, they create these non-performing loans in the banking industry, which bring about this financial instability that you saw in the charts. With respect to your first question, the model up to now is relatively stylized, meaning that it represents a sort of stylized global economy. What we are doing now is to regionalize the model in order to be able to at least characterize the growth trajectories that you might observe in developed economies vis-a-vis developing economies, and studying the different size of the damages that you might have in the two.
Thank you very much. I think we're almost out of time. I'm just tempted to throw a question to Michael as a central banker. I mean, would one implication of your results, do you think, be more concern about financial crises? Or, is there a potential link between your paper and Francesco's?
So I think that is an area that is many people are working on. Certainly, I think there are risks there. And I think it's something that should be studied very carefully. At the same time, when I think of the set of transmission channels that move from shocks to the evolution of the climate and shocks to the climate, so physical risks, the set of transition risks that may accompany a late transition or a disorderly transition, the type of things that Sandra talked about. I see many channels through which those could impact the real economy and financial stability. I also think that we really need to think hard about all of those channels. And one area that I would emphasize, which is a little different than your question, is I actually see a great deal of energy and a great deal of work going on the financial stability consequences of climate change, and at central banks and financial supervisors on policies and buffers to possibly mitigate the effects of climate change on the financial sector and instability through those channels. I think all of that work is super important, and I think there's an amazing amount of work going on in that area. One thing that I would like to emphasize, which you did not ask, is that work will be very effective in ensuring that the financial sector is resilient to the effects of climate change, not that the economy and that the world is resilient to the effects of climate change. And that I work on financial stability. I think it's really important to work on financial stability effects on climate change. I actually think it's much more important to work on climate change. And I really want economists, including economists at central banks, to really make sure that they're focusing on that issue in addition to financial stability questions, because the financial stability questions, while really important and really interesting, those will be taken care of if we address the economic challenges. And I actually think, maybe because central banks are fortunate to have great resources and great economists, that there are many ways in which they are accelerating work and policy work, and other parts of government and economics are not accelerating at the same pace. And I really encourage all macroeconomists to be thinking about the economic transitions, not just the financial stability ones. Although I do think it's really important, and I do think that the type of work, the connections between fluctuations in the economy and the impacts on the financial sector are something to understand, and that the type of work that Francesco did, maybe the type of work that I did on the real economic impacts, bringing those together will be valuable.
Great, thank you very much. We've overrun by a minute, so I'm going to wrap the session here. Thank the presenters for 4 very stimulating presentations. And a sort of final word from me is there are some very interesting papers behind the presentation, so I would urge you all in the audience to look up the papers by these presenters if you want further information, because I think they're very good reads. Okay, thank you very much, and I'll hand over to the next session.
Thank you very much, Dave. Good afternoon, everyone. My name is Elisa Lanzi, and I lead the modeling and outlooks work at the OECD Environment Directorate. Since this is a modeling workshop, to put things into context, we in the team operate a computable general equilibrium model. CG models have been left aside from the discussion in the workshop so far, so I'm hoping to squeeze them in this last session. So as we've had actually a great introduction to the last session with the last remarks from Michael, trying to highlight what the priorities are for the modeling community and what the next steps should be. So that's what we aim to do in this session. And in fact, so far we've tried to address different questions in this workshop. Yesterday, the focus was on tipping points and their economic consequences. And a few interesting challenges were highlighted. So for instance, the need to better link biophysical and economic models, or to solve the empirical puzzle on whether climate affects output levels or growth rates. And overall, how to make sense of a large body of literature on integrated assessment modeling of tipping points and social costs of carbon to inform policymakers. Today, we try to address a different question in the session that just ended, with a focus on the systemic risks in the economic system that come both from climate impacts and climate policies. And once again, we had very good insights and other challenges highlighted, such as the need to better integrate macroeconomic and climate policies, if not to actually consider them as the same thing, or the role of regulation and financial systems, including their role of consumer expenditures and the transition costs for both public expenditure and the financial system. So in this concluding session of the workshop, we'll be able to hear from 5 expert modelers and their views on how modeling can help to incentivize current policy action on climate change mitigation and adaptation, as well as engagements for future policy action. What will be interesting in this session is that the 5 panelists actually come from different modeling backgrounds, while all working on climate change. In fact, we have integrated assessment modelers, one expert on agent-based models, CG modeling, and DSG modeling. The experts also come from different contexts, so they'll be able to provide different perspectives on the subjects and the priorities to come. In fact, they come from academic backgrounds and research centers, central bank, and intergovernmental organization. So let me now please introduce the panelists. Karen Fischer-Vante, who is a professor of environmental and resource economics and public policy and director of the Institute for Sustainable Agriculture, Food and Environmental Science at the Pennsylvania State University. Karen has a large experience in integrated assessment modeling frameworks, including a focus on adaptation. Simon Dietz, who participated yesterday in the workshop, but for those who couldn't attend yesterday, is a professor of environmental policy in the Grantham Research Institute on Climate Change and the Environment, and the Department of Geography and Environment at the London School of Economics. Francesco Lamperti, who was in the previous session, but for those who just joined, is assistant professor at the Institute of Economics of the Sant'Anna School of Advanced Studies, and also a scientist at the RFF CMCC European Institute on Economics and the Environment. And Francesco specializes in ABM models, also coupled with integrated assessment. Rob DeLink, who's a senior economist at the OECD Environment Directorate and my longtime colleague. He leads the work on trade in the environment, but he's above all an experienced integrated assessment modeler with over a decade experience in CG modeling at the OECD. And last but not least, Valerio Nispilandi, who is an economist at the Bank of Italy with experience in DSG models. So I'd like to welcome our panelists, and to start the discussion, I would like to invite them to share their views on what they think the priorities are in terms of academic or applied research on analyzing the economics of tipping points and generally of climate-related systemic risks to the economic systems. If I can ask Karen to start, please.
Thank you. And I just want to thank you for the opportunity to participate today and yesterday. It's really been a great workshop and I've learned a lot. So I guess on the academic side, since I'm coming from that perspective, what I would say are some priorities in terms of where we should be focusing. And I guess I'm saying this because it's what I'm working on. So you have to take that with a little grain of salt. But I think capturing the explicit interactions across overlapping and intersecting networks it should be a focus. Yesterday's talks, there was a lot of talk about considering interactions between climate tipping points, which I completely agree with. And it was really great to hear Sandra talk today about economic tipping points. And so I guess that's kind of where I would be focusing on is, you know, we should be focusing in a similar way on interactions between sectoral or economic tipping points. What I mean by that is that, you know, you think of these things as overlapping networks. And so bad things can happen when you have these overlapping shocks or tail events occurring simultaneously across networks. One area that we've been looking at is the kind of coupled water power regional economic system, where you have one layer is your regional network of watersheds and basins is kind of one layer. And then you overlay that with the economic power grid as another layer. And that's important because the economic power grid draws water for thermal cooling and hydropower. So a water shock will create a shortage of water. for thermal cooling or hydropower generation. So you have these things kind of interacting with each other. And then you had the regional economy as a third layer. So you have, this reduction in electric power supply from the water shortage, as I just described. And you have that on top of increases in electricity demand due to temperature shock. And with that, those two things put together, you get unserved electricity demand. So when you think about the regional economic, kind of regional economy, so economic sectors such as manufacturing uses electricity to produce goods and services, as we all heard about. And this unmet electricity demand can result in impacts in the regional economy and importantly on welfare. So it's not just that you have these kind of overlapping kind of shocks and tail events occurring that are affecting other networks. Not only are they affecting each other within a network, within a certain geographic scope, but you have these things being, because they're networks, they're transported to other parts of the network, which is very interesting. We have a recent paper in Nature Energy that's coming out that's kind of showing that you could have, a shock occurring in a certain part of the Western power grid, yet you're seeing unserved energy occurring in another part. So those interconnected networks are really, really important. So I guess I'll stop there with those kind of introductory comments.
Thank you very much, Karen. And I think those are interesting remarks. It also leads back to some of the discussion yesterday in how to link more global models with local aspects. So if I can ask Simon, we continue with integrate assessment modelers.
Sure, thanks, Elisa. I hope you can hear me clearly. Good. So I want to group my initial remarks into 3 points, really. The first is that I find it really striking that over the last 2 days in a workshop on tipping points, how much of the discussion has been around estimation issues in empirical models of climate impacts. And I say this not because I think that emphasis is wrong. Actually, I think it's right. I think what it really reveals is the empirical turn that the climate economics literature has taken over the last 10 to 15 years. We're now generating tens, if not hundreds, of doctoral students every year who are earning their stripes by studying the impact of weather and climate on a particular thing in a particular place. And although I'm not an econometrician myself, and was initially, frankly, a little bit skeptical of this work, I think that it has left us in a vastly better place than we were 10, 15 years ago when we had these globally aggregated damage functions, no means to arbitrate over the curvature, very little data on which to fix the level at any particular temperature. And so with this impressive and growing body of evidence, we need to make best use of it, okay? And this leads on to my second point, which is that as far as integrated assessment is concerned and modeling the economic impacts of tipping points, the answer has to be interdisciplinarity or multidisciplinarity. So I really don't see how we're going to get a lot further in this area without building quite rich models which couple the best of the natural and physical sciences with what I've just described as being the best of the economic sciences. As economists, we've struggled for a long time with tipping points. I think, as Christian Traeger described yesterday, we treated them as synonymous with arbitrary catastrophes. And that was somewhat helpful in thinking about qualitatively about what a sort of a rational policy looks like in the face of a possible catastrophe, but it doesn't get you so far. So I think the answer here has to be interdisciplinarity, and I think that's also what Bill Nordhaus said in his talk. Lastly, my third remark, venturing cautiously into the area of transition risks and the macro side. Again, not my absolute specialism, but I would venture that what we need here a lot more of in this area is what could be described as short-run macro In other words, macroeconomic models which don't deal with smooth transitions to long-term steady states with low carbon emissions. We have a lot of those models. They've demonstrated that the transition is possible. They give us insights about what technologies we're likely to need, and so on and so forth. But in terms of thinking about the issues that Jean Pisani-Ferry raised, we need a lot more of the sorts of models, including what Francesco does, that can actually, but also, to be fair, I think DSGE models can offer a perspective on this too. So I'm fully neutral on the great debate here, Francesco. But these kind of models which have short-run dynamics and can actually really help us understand these relatively short-run processes, which could, however, generate large transition risks and things like supply shocks. So those are my comments. Thanks.
Thank you very much, Simon. And I would certainly agree with your comments, and particularly the part on the large body of empirical literature is really important. And we've done quite a bit of work ourselves in trying to link it within the CG model that has more sectoral details and can therefore try to maybe better incorporate the empirical literature. So with that, I'll pass on to Rob, who might say more about this. You're muted, Rob.
Can you hear me?
I was muted. Yes, apologies, everybody. Beginner's mistake, still happens. So I have a bunch of points to make. It's unfortunately not a nice short list like some. But first of all, I wanted to highlight that what we heard yesterday is Tim Lenton saying something. Well, some of these tipping points may actually be triggered already below 2 degrees. But then a lot of discussion went actually in the direction of how do these effects of the tipping points, how do these evolve? And I think for policy, it is much more important to talk about when the tipping points are triggered than about when the tipping points play out. So that's my first observation. Secondly, I think Dave said it in previous session, 3 to 4% of GDP loss in a few decades from now will not incentivize policy action. Who cares, basically? So then there's 2 ways you can go. One is, I think the media normally picks up on the boldest assumptions. You throw in all these growth effects, you find 80% GDP loss, and that will definitely trigger action. But that always reminds me a little bit about the evaluation of the Stern review. And sorry, Simon, if you're not okay with this, but I would say my consensus feeling of the Stern review was it was wrong, it was right for the wrong reasons. And I have a bit of so basically what Simon just said, this empirical literature, which finds these huge effects, it may be wrong. I think there's more and more evidence. I'm personally more on the side of Nordhaus, and that there might be something fundamentally that we don't know, basically what's going to happen beyond 2 degrees, and we can't say how these growth effects will play out, but they do incentivize action, and I think that's a good thing. But for me, the real answer is not about trying to find bolder numbers or trying to find scary things out there, but rather it's about how do we handle, as a society, how do we handle risk? How do governments handle risk? And shouldn't we talk about things like the precautionary principle? Haven't heard that at all yesterday or today. It isn't the role of the government to avoid triggering tipping points, avoid large-scale maladaptation, avoid potentially very large impacts in the most vulnerable areas. Michael Kiley highlighted downside risks clearly in the previous session. And if that's what you're talking about, if it's about avoiding kind of bad pathways, if that's, I think, our role also in policy advice, then you have to talk about regional differentiation, sectoral differentiation, and you have to look at the impact of climate change on poor farmers in India rather than only at office workers in Luxembourg, right? So we need to take both seriously. We need to look at regionally, sectorally, and for that you need welfare as a guiding principle rather than GDP. For that you need detailed models. So you need larger models basically to assess this. So with that, I think what we need to do is two things. One is we need to link across models. We need to link biophysical insights to real economy insights to the financial insights. It's not always easy, but it needs to be done. I was thinking a bit about when Francesco was talking about linking our CGE model to an ABM, and I was like, oh my God, we're doing so many of the same economic processes, but describing them completely differently, that it would be really hard to find a way in which you can do consistent analysis, where you describe the same economic processes in a consistent way across both models, yet still tease out the main advantages of both models. And it's clear that the ABM model can say something about innovation and under uncertainty, etc., that we cannot say in our CGE model. But at the same time, our CGE model has technological detail, it has sectoral detail that will be very hard to integrate in the ABM model. So maybe not only do we need to link models, we'll also need to do multi-model comparison exercises. I think if you look at the IPCC reports, the climate models do this. They know that you cannot publish in the IPCC and just say, well, we found one model and it came with this insight. That's not convincing enough. In the big process-oriented integrated assessment models, they also know this. They do all the time, they do this kind of model comparison exercise. But as economists, I think we're very well behind the curve. And I'm very glad to see that central banks are looking at the climate issue, because if we have a bigger group of modelers out there that do climate change analysis, I think we can get much more robust analysis. So what we need to do, and this workshop I think is a very good start of that, is talk more to each other, understand differences between modeling tools, but also run more of the kind of stylized scenarios where you really do some harmonization and you really compare models to find out which of your policy insights are actually model driven and which ones are really robust. I'll leave it there. Thank you.
Thanks very much, Rob. And indeed, in the hope to better talk to each other, I'd just like to invite Francesco so we can hear the perspectives of ABM modeling.
Thanks, Elisa. Yeah, let me start saying that I totally agree with Rob in saying that multi-model comparison are extremely useful exercise. And my feeling is that in climate and environmental economics, the field is much more open to this debate and to this comparison than, for example, in standard macro. And we have to leverage on this in order to run this exercise, because this might be extremely useful in order to see where models they provide similar insights and when they contradict one the other. I also share. I think I share one of the points made by Karen about networks. I have the feeling that both in modeling and in this new wave of empirical climate econometrics, we tend to think that what determines either the level of the growth effect is linked to the temperature experienced in the region. While it might be that because of the fact that production is dispersed in value chains, it might be that some particular shock that happens in one sector has huge cascading effect in others. And so I have the feeling that on one side, climate econometrics should move to the micro level. So trying to understand what are the effects within industry, within firms. And in the last year, for example, I've seen different papers, very well published, trying exactly to do this, taking panels of firms and trying to understand what is the effect of temperature anomalies or precipitation anomalies at the firm level. And then these might be fed into a larger model, whether a network model, an ABM model, a CGE, a DSG, whatever. And I also feel we have some theory to leverage on. For example, in the last years, we have seen the development of endogenous growth model based on production networks. We can try to leverage on these models and remove the growth engine that it's typically within the relatively standard AIM, which is either an exogenous growth model or a Ramsey model. My last point is on the joint study of physical and transition risks. So on one side, I have the feeling that, for example, the last IPCC report was telling us that tipping points and more in general physical risks, they might be there in a sizable manner also if we are able to commit to ambitious temperature targets. And on the other side, you have the feeling that transition risk, also because of political economy reasons, might slow down the transition. So at some point, these two risks might interact, and we need to understand how. And this is very much in line with what has been proposed by the NGFS, the last NGFS reports. And I think a lot of more research should be undertaken there in order to grasp better insights.
All right, many thanks, Francesco. So if we can end this first round with Valerio, I think we're all looking forward to hearing from you, since the perspective of central banks is quite unusual for us, but also your paper opens up a nice debate, which is linked as well with the recovery funds from COVID. So yeah, I'll leave the floor to you, Valerio. Thanks.
Okay, thank you very much, Alisa. So of course, as economists of the Bank of Italy, the usual disclaimer applies, and the following opinions do not necessarily reflect those of the Bank of Italy, nor of the Eurosystem. So as a central bank, of course, I wonder whether central banks should actually care about climate change. But as far as the environmental policies affect inflation and the business cycle, of course, I believe that central banks do need to develop a thorough understanding of climate change phenomena and of related tipping points. And let me give you an example. So in the next years, the price of carbon, will likely increase. Will inflation go up following an increase in inputs like carbon? Well, in a study forthcoming in the working paper series of the Bank of Italy, so with a colleague of mine, Alessandro Ferrari, we find a seemingly counterintuitive result. And we find that inflation will temporarily go down along this green transition. And the idea is that the implementation of a carbon tax, which is necessary for the transition, will permanently reduce future income. And other things equal, this drives a downward shift in the demand curve, resulting in lower inflation. Of course, it's possible that this result is parameter or model dependent, and that is why I think we need more research on this. But I also believe that there is another relevant research question that we should start asking. And as we all know, governments have the democratic legitimacy to take policies targeted directly to climate issues. But suppose for a moment that central banks do include in their mandate environmental goals. So my question is, are central banks able to implement effective environmental policies? But however, the research on what central banks can do to address climate change is for the moment relatively scant. And therefore, I would like to make very briefly some talks about what we know about this line of literature and about the huge room for research. So many academics, policymakers, and columnists have proposed a purchase of green assets by central banks, and some central banks are seriously thinking, or they already plan to do that. And as a macroeconomist, I think it's very intriguing studying the potential effectiveness of this green QE. And as Elisa said before, in another paper, always quoted with Alessandro Ferrari, we addressed this research question using a theoretical approach in a DSG model. And in that paper, we made a couple of points, leaving aside the problem of market neutrality, which, it is crucial, but for me, it's less interesting from a macroeconomic perspective. So first, to be effective at reducing global temperature, a green QE must be able to reduce the interest rate for green firms and increase it for brown firms. So the so-called Wallace neutrality the relevance of central bank balance sheet policies should not hold for the effectiveness of a green QE. Otherwise, the private sector will buy brown bonds until the brown yield comes back to the initial level. And actually, evidence suggests that the Wallace neutrality doesn't hold for standard QE policies. So the question here is mostly empirical. Are green bonds and brown bonds imperfect substitutes? And when and if central banks will start tilting portfolio toward green bonds, we could do serious empirical analysis on this important topic. And second, well, the long-run neutrality of monetary policy is a solid principle according to Macro 101. But climate change is actually a long-run phenomenon. So global temperature depends on the stock, also depends on the stock of atmospheric carbon, which is extremely persistent. And even if the central bank is able to affect the green-brown spread, Macro 101 and our paper suggests that it could not do it permanently. So, of course, there is also recent research, both theoretical and empirically, that is indeed finding monetary policy non-neutrality in the long run. So the argument goes as follows: if a temporary monetary policy affects investment in R&D, the effect on real activity is permanent. Similarly, but now I'm really not aware of studies out there, so there is a lot of room of research, if a green asset purchases boost investment in new green technologies, we could actually see some long-term effects on environment. And let me conclude with two other options that have been discussed. So on top of green asset purchases, another option is to assign a preferential treatment to green bonds in the central bank's collateral framework, as some central banks are already doing. And the purpose is, of course, is closely split to that of a green QE, so reducing green and increasing brown interest rates. And Francesco Giovanardi and his co-authors at the University of Cologne have made some steps in this direction in a theoretical model. And finally, and I conclude, an additional option on the table is a policy measure just announced by the Bank of Japan, which will begin making loans under a new scheme to target projects aimed at dampening climate change. Again, also here, there is a lot of room for theoretical research to explore the transmission mechanism of these policies and for empirical research to assess ex post their effectiveness.
Thank you very much, Valerio. So hearing you talk, I feel there is a fair amount of agreement on the need to look at the short-term transition costs. But that doesn't take away from the fact that climate change is a long-term issue. So the long-term perspective such as that can be provided by an integrated assessment model or a CG model is still needed. So, I mean, we've heard from Francesco, and that's one approach to merge the shorter term issues and with the longer term, but how would you approach this otherwise? Does anyone have ideas on how you could better incorporate the transition risks also in longer term models? Because that's one challenge as well of DSG models, that sometimes they only address the short term. So they're very useful in that respect, but it's still needed to look at the long term as well for climate change.
Okay, thanks, Elisa. No, let me disagree on that. So, yeah, I mean, DSG models have been a lot used to study issues like the business cycle and the effects of monetary policy. But another possible use of DSG models is to study, the transition from one city state to another city state. And of course, you can study you can study what happens during the transition. The transition could last for for 1 century. So yeah, I mean, I think the DSG model also can be used for studies long-term issues. And yes, and what so in my green QE paper, yeah, we studied just the business cycle, but yeah, you could study also structural changes to the economy.
Yeah, thanks very much, and that's a very important point. And I do think the DSG models are very useful to that respect. So maybe, however, if we can get yeah, Rob, you wanted to add something?
Yeah, I would just say that I think the long-term modelers can learn a lot from DSGE models and similar macroeconomic models, in the sense that the modeling of capital is not very advanced in a lot of our models. At least not, we have capital vintages, etc. But the models, the CGE models at least, are really tailored towards these long-term effects. And therefore, they're very hard to look at short-term shocks. They don't understand, they cannot say anything about how interest rates are affected by this. And interest rates, of course, in integrated assessment models, interest rates would affect discount rates. And if we're talking about discount rates, we're back to discussion on tipping points. So I think, whenever I talk to other modelers, it's very often when we talk about widely differing perspectives on whether a policy is actually good for growth or bad for growth. And when you dive into the details, 90% of the times it comes down to basically whether you assume that green investment crowds out other investments or not. And CG models just make an assumption on it. They just assume, well, no, there is going to be no crowding out, so the investment is going to boost growth, and the extra growth is going to be beneficial. That's what the non-equilibrium models tend to assume that as a default. The neoclassical models as a default tend to assume that any new investment crowds out other investment, and therefore it is costly for the economy to adapt to this green investment, and it has to reduce other types of investment. So by learning more from kind of how does the economy, how does the financial economy work in that respect, and how do we understand how investment plays out, I think that's one of these typical low-hanging fruits that we can reap off.
Right, thanks very much, Rob. I wanted to pick your brain also on another question that you raised, which is the raising empirical literature and how that can be used to support modeling and calibrate models, etc. But there is, however, a challenge that comes up in this, and it's the fact that very often the levels of policies and of climate change that are coming for the future are not quite the same as what's happened in the past. We're turning into like much more frequency of climate extremes, of stronger climate impacts, but also of, for instance, carbon tax levels that wouldn't have been, they were not present in the past. And yet the empirical literature is based on past data. So how, as modelers, do we really base projections on past estimations? There's like a mismatch between the ex post estimates and ex ante, especially in views of climate policies that could be very different from ones we've had in the past. Maybe if I can ask Simon, since he mentioned this.
I'm happy to make a start. I mean, I think this is a really important issue, and it's one of the main caveats, I suppose, that we might apply to using the empirical literature when making projections. So basically, in a sense, extrapolating out of sample, at least when we think about it in terms of historical global averages. Actually, if we're extrapolating at the country level, we might not always be extrapolating out of sample. And the potential sources of bias actually go both ways. So Elisa, you mentioned the fact that, in the future we would experience more frequent extremes and so on. But at the same time, that those will be visited on a more technologically advanced economy with a smaller agriculture sector than was the case for the whole of the historical period on which the data were estimated. So it's not actually clear which way the bias goes. And this is where I start to run out of road in terms of knowing what's the way forward. I have started to see some papers coming out which have looked at the you're trying to get at the stability of the relationship over time in the historical period and how it might have changed. I think also, researchers are becoming increasingly creative in trying to think about this. So there are a couple of recent papers using spatial rather than temporal first differences to actually think about trying to get more out of the cross-sectional data and say more about the kind of the effect of long-term change. So as we get past the first generation of studies doing the kind of mostly harmless climate econometrics, the kind of diff in diff with we're getting more and more interesting things, looking at mechanisms, looking at and that helps us get towards these issues, but it's not easy, and I think you're right to identify it as being one of the main worries about using empirical estimates in projections.
Right, thanks, Simon. If I can maybe ask for Valerio's perspective on this, in the sense that at times when you look at country level, the empirical data is richer. Do you think that would be the case, or is it still very challenging to calibrate models even at national level?
Well, calibrating the macroeconomic DSG model is difficult. So when you have also the environmental part, of course, this is going to be even harder. So I think what in this case, what the DSG model can offer is first of all sharp economic intuitions. So if the DSG model are, small enough, they can offer very clean and transparent economic intuition, even if the calibration, is not totally serious. Or if you really want to go quantitative and want to estimate the model, well, then you can, use you can go empirical, and you can take the model to the data, and then you can use Bayesian methodology to have a distribution of impulse response functions. But here, yeah, I'm less expert on this, less expert of DSG estimation, so I can really cannot give you an answer on which kind of data you can use to estimate the DSG models. Of course, for environmental purposes.
Okay, thank you. Anybody else wants to say something on empirics and how they can be used for models? If not, I'd like to maybe go back to a remark that Professor Norris made yesterday, which was the claim that models should mostly focus on mitigation because adaptation is more of a private matter. And I think that's been a matter of debate, and especially some models have actually focused on adaptation as well because of its relevance in terms of the amount of public money that's invested in adaptation. Looking, for instance, at the adaptation fund, but also public money that's been invested in different countries in terms of resilience of its infrastructure. So I was wondering if you had some insights maybe on how to better capture the risks of adaptation, possibly adaptation tipping points, and the need to increase the resilience. Resilience already came up in terms of the financial systems, but as it's been said already, it's really important that it goes beyond just the financial system and throughout the whole economy. So maybe Karen, if I can ask you about this.
Sure. Yeah, there's lots of things that came to my head when you asked that. First of all, I don't think just this is kind of a separate point, but I don't think adaptation and mitigation should be thought in terms of isolation from each other, because I think maybe one point you're alluding to is that your ability to mitigate is going to depend on your vulnerability, which will depend on how well you can adapt to climate change that's occurring. So I don't think you can say we should focus on one or the other. I think they're interconnected as always. So in terms of, I'm sorry, I kind of got I was focused on that. And so what was your final question so I can? Yeah, multiple parts of that.
Yeah, sorry. I think it was just on how models should focus on adaptation, and that's indeed already a good answer in terms of looking together at mitigation and adaptation. But yeah, it's just.
Oh yeah, okay, yeah. So the other thing I was going to point out, and one thing that we're so you know we've had funding from the Department of Energy, Office of Science for the last 5 years, and we just got renewed for another 5 years. And in the first 5 years, we were focused on building these modeling frameworks that I kind of described, that where you're capturing, you're basically having these process models with overlapping networks, so you can retain the spatial, temporal, and sectoral detail in each one of them, which is important for extreme events. But what we're doing in our next 5 years is applying machine learning techniques to try. So now that we have this kind of computationally intensive coupled modeling system, you can apply machine learning techniques in these modeling frameworks to identify pressure points in the coupled network system. And that allow you to identify kind of the stressors and kind of the areas that are most problematic. You know, we're of course looking at the US and not at the world. So you can look at, you know, kind of where are the pressure points in this network, and including what happens when these hazards are compounded. And then, you know, ultimately, and this kind of gets to some of these other questions, is you essentially want to be able to do uncertainty characterization and quantification analysis. And when these models get more complex, it gets harder and harder to do that. So one thing that we're looking to do is, through this kind of machine learning techniques that we're going to apply, we can identify what part of this complex modeling system can we simplify. Can we use an emulator or some sort of reduced form to simplify that so that we can do UCUQ analysis? So I think that's kind of, at least in terms of trying to get at adaptation, is really important to know kind of temporally, sectorally, and spatially where these hot spots are going to be. So I guess that's one of the answers to your question.
It's an excellent, and indeed highlighting again also the need to go more spatial, which is particularly relevant for adaptation, of course. Rob?
Yeah, if I may come in here, I think you raised two issues that are both very important. One was on adaptation, where I think there is a significant role for actual economic analysis, because even if adaptation is a local decision rather than a global decision, it is still very much something that you cannot just assume away by saying, oh, actually everybody is going to adapt optimally. Adaptation breaks down if we have runaway climate change. Adaptation breaks down for tipping points. Adaptation requires massive government investments. Think about building seawalls. You know, these things don't happen. Adaptation depends crucially on your pathway for mitigation. If you know you have an advanced mitigation policy that is credible, you will only build your dikes a little bit higher. I'm Dutch, so the dikes are an actual example. You build a little bit of a higher dike. If you know that it's very unlikely that you can provide a very stable mitigation signal to the community, you will start building your dikes a lot higher, because it's much cheaper to one time build a much higher dike than to keep building your dike, increasing your dike every 5 years for whatever policy inaction you have. So I think it is very much a government issue. It's an investment issue. It's a financial issue. It's an international finance issue with the $100 billion that you mentioned. So there are all these elements there that you just cannot assume away in saying, well, this is going to be optimally organized, and let's just focus on what people do for mitigation. But if I may, I know my answer is long, but I wanted to raise also a point on your second point, which is resilience. And I think that as economists, yes, we need to talk about ecosystem resilience, we need to talk about biophysical resilience, but I wanted to actually take this point on resilience also to talk about economic resilience and talk about how we can use our models to show that, for example, you need international trade in order to make sure that your consumption systems are resilient to extreme weather events and stuff like that. So I'm on trade and environment, my pet topic. But resilience is hugely important, and international trade is hugely important in ensuring domestic economic resilience. So again, to just say, if we do modeling, and I know a lot of climate modelers understand we need global modeling, but really national analysis on climate change doesn't make sense. You need the international context there.
Thanks, Rob. I think Francisco wanted to add something.
Yeah, I mean, in the end, I wanted to say something very similar to what Rob just said. So I also have the feeling that adaptation is largely dependent on public intervention, both because I tend to think about adaptation as infrastructure, as, for example, retreat in coastal zone in some cases, and also because I think there is a lot of research that should be funded in order to better organize adaptation, and in the end, it will probably be public research. So on the modeling perspective, I have the feeling we should try to find a way to include infrastructure in our models and to better model decisions by the government. So to detail better how the government runs fiscal policy and what are the interactions between climate and fiscal policy, and probably also to include some political economy consideration to see whether then the government, when the government is willing to undertake certain decisions rather than not.
Yeah, thanks very much. So speaking of a country perspective, to which I agree, and lots of countries are currently discussing how to increase resilience and the resilience of their infrastructure. I was wondering if Valerio thought that his type of modeling approach could be extended to look at this type of expenditures as well.
Of course. You know, I agree with Francesco in particular on the fact that we need to include political economy constraints in the model, in our models, and agree with you on that. Yeah, we need to include public infrastructure in our model to understand the economic effect on climate change. But let me also add, I would like to come back to the adaptation. So I think another very important topic that we should start studying is the heterogeneous effects of the green transition. So I mean, you know, the ZHANG model in particular usually have been always like a representative based model, but now, yeah, they start to include also heterogeneous agents, and I think, yeah, the green transition will affect some households, will maybe benefit other households. So yeah, we should also include heterogeneity issues in our considerations, and these heterogeneity issues will be, of course, affected by political economy problems.
Great, thanks very much. Well, we're getting towards the end of the session, and like very often when modelers talk, we come up with tons of ideas on lots of things that we'd like to do. Go more spatial, consider more sectors, link short-term and long-term, but unfortunately we often can't then get to do it all. And it's one project at a time, let's say. So to wrap it up, if you had to, each of you give like one call for the modeling community, or like pick the one project you'd like your PhD student to focus on, with the purpose to help governments to incentivize short-term policy action on climate change, what would that be? Maybe I'll follow the same order as the start and ask Karen to start.
Okay, so in terms of, yeah, I think your point about the next generation, because that's kind of at least getting old enough to think about the next generation carrying on this work. So that training of that, and I think somebody brought this up, is that we need to be training people to be doing this kind of work. And I think, you know, I mean, we're trying to do that at Penn State and the other universities that I work with. We're trying to do that. That's really, really important, because we just having, and I think all of us would agree that, you know, kind of this ability to combine models, whether it be because you have an ABM with a CGE, with a growth model or something, you need to be able to kind of, and in my work in terms of putting the water balance model with the power system model with the CGE model, you need to be able to do that work. And yet in the past, we've always worked in kind of isolation from these other disciplines. So I think training that next generation of scholars, and in particular, you know, from experience, it's been very, very difficult to couple these models. Much simpler to say it than to do it. And what we have found is that we really need to employ kind of software engineer, computer scientists to help us do this work. You know, grad students are not going to be able to do it, we found. So we have to hire, you know, we have to get not only people in earth sciences and economics, sociology working on these issues, but also computational people, because what we're talking about requires high performance computing and coupling of models, translational software. So that's a long answer to your question, but that's where I think we need to be going, at least to be able to do some of the work that we're doing.
That's a very good point. It's hard when you graduate from economics and all of a sudden have to also become very operational on tons of programs. Simon?
Yeah, I'm much impressed by that point. I'll just echo it. I think that the set of skills we have here is actually not widely found. I think that you know, one of the side effects of the empirical turn in economics, which I think has left the discipline in a much better place than it was, is, however, that about 9 out of every 10 PhD students that I see are econometricians and are capable of doing certain kind of study. But when it comes to building quite rich models that integrate across different fields, that's actually not necessarily the right skill set. And as Karen said, I mean, I'm lucky enough to have a co-author in James Rising, who used to be a software engineer before he became an environmental economist, and can do stuff that the rest of us just sit back and go, whoa, how did you do that? And it only seems to take him a few hours. And so this sort of calls for a bit the rise of computational economics, and also the kind of borrowing ideas across disciplines, across fields. Been having some interesting chats recently with people about optimizing rich models, and there seem to be as many answers outside of economics than there were actually within economics, which emphasizes the importance of actually casting the net quite broadly when looking how to make progress.
Thanks, Simon. We're also lucky to have a couple of people who are very good with the computational skills. Well, Rob, in your case, the PhD student question doesn't work, but what would be the low-hanging fruit for improving modeling for you?
Yeah, I was just about to say that I think Karen already nailed it on the training needs. In terms of what I think we need to advance on policy advice is really robust analysis on the benefits of early action. And for that, we need this connection between the short-term models and the long-run models. We need to show how bad things get if you don't act. We need to show how bad it is in terms of stranded assets and financial risks if you suddenly decide after 20 years you did want to stay below 2 degrees. So this idea of wait and see is a bad one, and we need to build a robust case to avoid that. And I think if we manage to do that, I consider my job done, basically, because this is the crucial one for me.
Thanks a lot, Rob. Francisco?
Yeah, the smart ideas were already taken. So I come back to one of one of the points that I made before. So going to the micro, if someone is interested in empirical stuff, try to use micro data in order to better disentangle the mechanisms that might link temperature anomalies or whatever physical driver to economic consequences. And if someone is interested in modeling, I would go toward the direction of building up production network-based models with a lot of spatial heterogeneity and sector heterogeneity.
That doesn't sound like an easy challenge. We are looking forward to hearing about it. And Tuan, Valerio?
I really agree that, yeah, we really need the skills of computer scientists to simulate these complex models. But I invite you to not forget the importance of very simple economic intuitions that are able to easily communicate to policymaker, to the public, the importance and the key points of our research.
Thank you very, very much. Well, with that last remark, I would like to close the session as it's time. And I would really like to thank the panelists for providing much food for thought and inspiration for the modeling community. So thanks very much, and I'll pass on to Shardul to conclude.
Thanks very much, Elisa. And after that fascinating discussion over the last hour, when people with much more expertise than me have already provided a lot of discussion in terms of future directions, I'm not going to make any substantive points right now, because I feel like the family dog after Thanksgiving dinner. There's not much meat left in the turkey at this point. So just a few final thoughts, not on the substance. When we came up with the idea of connecting to somewhat distinct areas of tipping points in the biophysical climate system on the one hand, and climate-related nonlinearities in socioeconomic systems, we did not expect that it would resonate so much with both the experts we reached out to and the participants from around the world who registered to attend. So a huge thanks to such an excellent cast of speakers and to our participants for your perseverance through 2 days of modeling discussions. We've averaged anywhere from 300, 330 participants or to 200, and slowly going down to 120, 130 right now, and that's really impressive and shows what kind of a chord this topic has struck amongst all of you. In terms of next steps, once we have permissions from the presenters, we will aim to put the presentations on the web, and we'll look into the technicalities and permissions also to see whether we can put the session videos online. And of course, we'll be in touch with the speakers on that, because there's been a lot of demand already to be able to access the sessions from people who could not participate. There will be a report from this workshop and possibly a collection of papers depending upon the availability and interest from our panelists. Third, within the OECD, we will be reflecting on this workshop, both within the Environment Directorate, but we had a number of colleagues from the Economics Department in particular, as well as from other parts of the House who've closely followed the discussion. And modeling on climate change and the climate economy linkages is an area which is a really high priority for us. So there'll be a lot of internal reflection that'll follow in terms of how to carry this work forward. Fourth, I don't see this as the end, but the start of a highly policy relevant conversation. And I encourage you to reach out to us if you have relevant work or ideas to share, and we can see how to take all that forward. In terms of where to access materials from this workshop, it's the same website you registered for the conference, and that's very simple. It's oe.cd/climate tipping, one word. And finally, such an event would not have been possible to put together without the help of several colleagues. Let me thank some of our key colleagues from the economics department, Chief Economist Laurence Boone, Dave Turner, who were both on the agenda, as well as Alain Desser, who's been a close partner in this work throughout. And from the Environment Directorate, Director Rodolfo Lassi, who you heard from yesterday, Andrew Pragg, my colleague, and colleagues from my modeling team, including Rob Delink, you just heard from, but also Eleonora Mavrodi and Jean Fourret, who were active behind the scenes. I'd also like to thank Ilyas Mousse-Iye and Emily Seftel for their support. And last but not least, let me express my special thanks to the dream team of Elisa Lanzi, Elia Costa, and Norbert Monti, who were really co-conspirators in crime in helping conceptualize this workshop and worked tirelessly to line up such an excellent list of speakers, and have been playing a critical role throughout the past 2 days. So with that, thank you, everyone, and look forward to being in touch with as many of you as possible as we scope out the next steps. Goodbye from Paris.